Hey, hello everyone. So this is a question from a book called KROTOV, which is essentially a collection of physics Olympiad problems. So let's see how we can go about this problem here. A metal jumper of mass m can slide without friction along two parallel metal guides directed at an angle alpha to the horizontal and separated by a distance b. Okay, so we have this kind of frame here, and the jumper which is being talked about is this. The guides are connected at the bottom through an uncharged capacitor of capacitance C, which is this, and the entire system is placed in an upward magnetic field of induction B. So the upward magnetic field is in this direction. The magnetic field is not perpendicular to this plane, it's just directed upwards. At the initial moment, the jumper is held at a distance L from the foot of the hump. Okay, so this here, this distance initially, this is L. Determine the time t in which the released jumper reaches the foot of the hump. What will be its velocity Vf at the foot? The resistance of the guides and the jumper should be neglected. So let's see how we can analyze this problem. First, let's draw the frame. It makes an angle of alpha with the horizontal, and there is a capacitor, capacitance C, present here. Then we've got our jumper, and this length here is B. The initial distance of the jumper from the ground is L, and the magnetic field is in the upward direction. Right? Yes. Now, let us observe this assembly from this angle. So if we see the assembly from this angle, we see the jumper from its cross section, and we see that the jumper is placed on kind of an inclined plane. So the forces acting on this jumper, first of all, the the gravitational force, mg. Now, because everything is taking place like in an inclined manner, we should just take our x and y axis to be inclined like this at an angle of alpha with the horizontal. So this is our choice of axis, and if I break this mg into its components, so if g is right here, then this angle is alpha, so this component here, this should be mg cos of alpha. Let's remove this mg here, and then this component should be mg sine of alpha. Right? Now, this ain't the only force which is acting on this. You feel that if this jumper is coming down and there's a magnetic field in the upward direction, there is some kind of magnetic flux linked with the region I'm shading, right? And as this jumper comes down, this region decreases in its area. So first of all, this length L is not constant because the jumper is obviously coming down. So let's say that any instant, the distance between the ground and the jumper is x. Let's just say that this is a general instant. At this point, the area of this shaded region here should just be x times b. So b times x is the area of this shaded region. If we write the flux, magnetic flux for this, we get bx, which is the area, times the magnetic field, which is perpendicular to the plane of the area. Let's just say that the field perpendicular to this area is B naught. It's not exactly B because B makes an angle. B makes some kind of angle with the plane. So let's just say that this is our magnetic flux. Now the EMF, which is induced in this loop here, which is formed by the jumper and like these three portions, is the derivative of this flux with respect to time. So we get the derivative of Bx B naught with respect to time. Now you see that B and B naught are constant. They do not change with time. But X, however, changes with time because the jumper is coming down. So this distance decreases. So we get B naught dx over dt. Now, let's say that the jumper has some velocity v here. If the jumper has a velocity v, then we can say that dx by dt is the derivative of the displacement with respect to time, which is equal to the velocity. So we can say that the EMF induced is equal to B naught times V times B, right? Okay, so if this is the EMF induced, are we given the resistance anywhere? No. Okay, never mind. Okay, so this is the EMF induced. Now let's come to our capacitor. So this is the EMF induced in the loop. Now the capacitor here stores charge. So the charge stored in the capacitor is equal to its capacitance times the EMF. So the charge stored is capacitance times the EMF induced in the loop, which is equal to this, B naught VB. So we get C B naught VB, which is the charge in the capacitor, right? Yeah. So this is Q. And suppose now we want the current which is flowing inside the loop. How would we find the current? Because if suppose we had a resistor, we could just divide the EMF by the resistance and apply Ohm's law and get the current. But right now we don't have, like, we're not given the resistance of anything, so we know the current is the derivative of charge with respect to time. So I think we can just differentiate this expression with respect to time. So if I differentiate this expression with respect to time, we get derivative of C B naught VB with respect to time. Then dq by dt is just I, the current we are looking for. C, B naught, and B are constant. So we can just take them out of the derivative, and we're left with dV by dt. Right? And this is dV by dt, let's just call it W for acceleration. So the acceleration of this is W. So let's just mark this acceleration here as W. And now, also there's one another force which is working, and that is the magnetic force. Because there's current in the jumper, and magnetic force is like this in the upward direction. The magnetic field is in this direction. Then according to the law of cross products, a magnetic force should act in the direction upward the incline. So the magnetic force should act like this. The magnetic force is equal to B times I times L. So let's just put our b naught here, and then I, which we have found out to be this, c b naught b w times the length. The length of our jumper is b. We get b naught squared c b squared w is equal to the magnetic force. Right? So we've got a magnetic force here, and we know that the acceleration of our jumper is w. So we can just apply F equal to ma for these two forces. So if I just say that mg sine alpha minus this force b naught squared c b squared w is equal to mw, we can calculate the value of w from here. So mg sine alpha is equal to w times m plus b naught squared times cb squared, and w comes out to be mg sine alpha divided by m plus b naught squared cb squared. So that is the acceleration, and what we were asked is to determine the time t in which the released jumper reaches the foot of the hump. Okay, so we've got our acceleration now, and we've been given that initially the jumper is at a distance of L from the ground. So we just need to calculate the time it takes to travel this distance L if it has an acceleration W. So we can just apply the equation of motion here. So this is the equation I'm talking about. The distance which has to be traveled is L. The initial velocity is 0 because it is coming from rest. So this term just cancels out to be 0. And for this term, we got half times a, which is the acceleration, which is w, and t squared is what we have to calculate. So rearranging everything, we get t squared is equal to 2l divided by w. Then t is equal to root under 2l by w, which comes out to be 2l divided by mg sine alpha times m plus b naught squared c b squared. Right? Now, see that we've not been given the value of b naught in the question, but we have been given the value of b. So, our b naught is the component of the magnetic field, which is perpendicular to our incline. So let's just try it here. So our b is like this, and we want the component of that field perpendicular to our plane. So you can just calculate that using trigonometry. This is 90 minus alpha, this angle, and we want this angle here, this angle, right? So this angle here is also 90 minus alpha because these two are vertically opposite angles, and then this component is normal to the plane of the incline. So this angle here should be alpha. Hence, this component here, which we are calling b naught, should be equal to b times cos of alpha. So putting b naught is equal to b times cos of alpha, we get t equal to root under 2l times m plus b squared cos squared alpha times c times b squared divided by mg sine alpha. So this is what the time is coming out to be. There was one more part to this question. What will be its velocity vf at the foot? So to find the velocity, we can just apply this equation. The initial velocity is just 0. So v is equal to acceleration, which is w, times t. So from here, we can find the value of v2. So yeah, thank you guys for watching the video, and tell me if you like content like this.